Welcome to The Explainer. Today, we are going on a journey to a place smaller than you can possibly imagine, but it's a place that holds enough power to build entire stars and to fuel our world. Yeah, we're gonna unlock the secrets hidden right inside the atom's core. Okay, so let's just jump right in with a huge puzzle. You've got the nucleus of an atom, and it's absolutely crammed with protons, which are all positively charged. Now, everything we know about physics says these things should repel each other. I mean, violently. The whole thing should just fly apart. So, what is going on? What force is holding it all together? To get to that answer, first we really have to wrap our heads around the scale we're dealing with here. The density, the size, it's truly unlike anything in our everyday world. So, I want you to picture this. Imagine an entire atom is the size of a giant football stadium. Okay, you got it? Now, the nucleus, the part with basically all the mass, that would be a single marble, just sitting there in the middle of the field. And the density of that little marble, it's just mind-bending. If you could somehow scoop up just a single teaspoon of that nuclear matter, it would weigh around 1 billion tons. I'm not kidding, 1 billion tons. So, let's think about that. Whatever force is holding that stuff together, it has to be the most powerful thing in the entire universe. And, well, it is. And the hero of this story is called the strong nuclear force. Now, what's so wild about it is that it's actually a kind of leftover force. See, the real strong force is deep inside, gluing these fundamental particles called quarks together to make protons and neutrons. But a tiny bit of that incredible force kind of leaks out, and that becomes the glue that holds the whole nucleus together. Now, this force, it plays by some really weird rules. It's the strongest force we know of by a long shot, but it only works over unbelievably short distances. We're talking a few femtometers. And what's really cool is that while it pulls things together really strongly, if you try to push them too close, it suddenly becomes repulsive. It pushes back. And that's what keeps the nucleus from just collapsing in on itself. All right, so how does this all connect to probably the most famous equation ever written? This isn't just theory. This binding process is the very source of all nuclear energy. So when these protons and neutrons get pulled together by that nuclear force, they release a huge amount of energy. We call this the binding energy. Think of it like this. It's the energy that's now holding them together. And if you ever wanted to break them apart again, you'd have to put that exact same amount of energy right back in. But wait a minute. Particles come together and suddenly, poof, a ton of energy appears. Where on earth does it actually come from? And here is the absolute craziest part. The energy comes from mass. It's true. If you were to weigh a complete nucleus, it would actually be a tiny bit lighter than all the individual protons and neutrons that you started with. A little bit of their mass has just vanished, and we call this the mass defect. But that mass didn't really vanish. It was converted directly into all that binding energy. And it follows this exact formula. The energy you get out, that's E, is equal to that tiny bit of missing mass, m, times c squared, the speed of light squared. And here's why that matters so much. C squared, the speed of light squared, is a ridiculously huge number. So that means you can take a tiny, tiny amount of mass and convert it into a colossal amount of energy. That's why nuclear reactions release literally millions of times more energy than a chemical reaction, like burning gas or coal. So this amazing principle, turning a little bit of mass into a lot of energy, it gives us two totally different ways to tap into the power of the atom. It really all boils down to stability. Turns out, the nucleus of an iron atom is pretty much the most stable, tightly bound thing in the universe. So you can get energy by taking really heavy elements, like uranium, and splitting them apart to get closer to iron. That's called fission. Or you can take really light things, like hydrogen, and smash them together to get closer to iron, and that's called fusion. Both roads lead toward more stability, and both release that binding energy. Now, fission, splitting atoms, that's what we use in today's nuclear power plants. It works great, but it does create some nasty, long-lived radioactive waste. Fusion, on the other hand, is what powers the sun. It's basically the holy grail of clean energy because its fuel is just hydrogen, which we can get from water, and its main byproduct is just harmless helium. Okay, now let's just zoom way, way out for a second. Because these same exact processes aren't just for making power. They are literally the reason everything around you exists. The whole story starts right after the Big Bang, which created basically all the hydrogen and helium. Then, for billions of years, stars act like giant fusion reactors, cooking those light elements into heavier ones, all the way up the periodic table to iron. But if you want to make anything heavier than iron, you need something even more extreme. You know, the calcium in your bones, the iron in your blood, all of that was forged in the heart of a star that died long ago. But what about the gold in a wedding ring? That was made in the unbelievable violence of a collision between two neutron stars. And get this, in 2017, we actually saw one of these events happen for the first time, confirming exactly where all that stuff comes from. Just incredible. Okay, so this isn't just about ancient cosmic history. We figured out how to harness the power of the nucleus, and it's become a huge part of our modern world. Think about it. Nuclear power provides about a quarter of the world's low-carbon electricity. In our hospitals, radioactive isotopes in PET scans let doctors see what's happening inside our bodies, while focused radiation can destroy cancer cells. We even use it to look into the past, with carbon-14 dating telling us how old ancient artifacts really are. And that brings us to here. We've gone from the puzzle of why the atom holds together to the cosmic forges that build the elements. We've figured out the fundamental force that builds the universe. And that understanding gives us an immense power and a profound choice about how we're going to use it.